everyone. Paul McKenney will be speaking on scalable updates. So if you're not familiar with Paul, shame on you, number one. So Paul has been doing multi-core stuff for longer than I've been alive, which blows my mind, and is behind a lot of innovations, including RCU. If there is a Yoda in parallel computing, at least in the context of multi-core, Paul would be Yoda. So take it away.
Overwhelmed I am, or something like that. So talk a little bit about scalable updates, scalability in general. The Issaquah challenge, we'll talk about the laws of physics, and I think we'll hear more about that. We've heard a little bit about it this morning already. We'll talk about some special cases. Updates turn out to be a little bit problematic for the laws of physics, it turns out. And we'll look a little bit about some things that I've been doing with some other people on trying to get around those laws. Sometimes you have to dodge the laws of physics is what it comes down to. So the Issaquah challenge, this gets its name from a C++ Standards Committee meeting in Issaquah, which is near Seattle, Washington. There is transactional memory that is part of a technical specification, which is sort of a staging area for the actual standard itself. I was participating in that. And they were going through and getting ready for a presentation in the main group. And they were talking about, yeah, okay, so here are some things we do with transactional memory you just cannot do with locking or other techniques. And I'm kind of biting my tongue because, you know, I don't want to disrupt the proceedings. But this is an evening session, it's getting later, and it's getting harder and harder to stop from just bursting out and saying, but you could. Anyway, at the end, the guy says, okay, I think we've got a good story. The one thing we're lacking is an actual implementation where you'd actually do this stuff without transactional memory. Paul, would you like to take that on? And I'm going, yeah, actually. So a lot of this is an outcome from that. It's not like I know of any practical applications at this moment for this stuff, but it was something that came out of a challenge, it's been a lot of fun, so I guess I have no complaints. The challenge was this. You got a pair of binary search trees, and we've got a couple elements. So the tree starts out that the left side one has 1, 2, and 3 in it, and the right-hand side one has the 2, 3, and 4, and that's why the 1 and the 4 are light on the other side. And what you want to do is you want to move the elements. So you want to move element 1 from the left side tree to the right side tree, atomically. And that means that if somebody searches the left-hand tree and doesn't see the 1, if they immediately go and search the right-hand tree, they better see it. By the same token, if they search the right-hand side tree, the one where 1 is going to, and they see the 1, they better not see it when they immediately search the other tree. So what we mean by atomic is nobody can prove that there was ever a time when there was either no 1 in either tree, nor can they prove that there was a time when 1 was in both trees. So atomic in that sense, kind of a file system move sense. And the other piece of the challenge was that if you're moving 4 in the other direction, you'll notice that there's no nodes in common. You know, they have different parents. So in theory, there should be no contention between the two moves. And part of the challenge is to actually implement it so there is no contention. So you're moving in both directions, okay? So you don't want any contention between the move operations. In other words, you just move one, move the other, and there's no conflicts and locks. Nobody's trying to do atomic updates to the same memory locations. Nobody's trying to write to the same memory locations, all right? So no contention. And of course, that means that a lot of the standard approaches you do with locking just need not apply for this. For example, if you're doing some kind of two-phase locking where you lock your way down from the root, well, both sides are going to lock the root, so that one's out. Forget it. You could, standard thing is just to apply a lock to each tree, but then you need both trees locked for both of them. Can't do that, all right? So you have to do something a little bit different. And this has had a little bit of history. This challenge showed up a little over 2 years ago. And I had a kind of a crude first solution that I did as a C++ Standards Committee member. That's the N4037. You can look that up if you want to. It's obsolete would be a good way to put it. On CPPCon, a few months later, I actually did one that scaled sort of reasonably. And then a few months after that, at LinuxConf AU, I had one that actually had decent scalability. The nice thing about it was you could take the text applications, take a tree search, take a hash table, whatever, make some very small modifications to it, and have something where you can do these atomic moves. The reliability was kind of okay. We'll talk about reliability later. I have kind of a different approach to reliability based on what I have to do in the Linux kernel. Now, what we're doing here, Dmitry Vyukov, he's a guy at Google. He's the guy behind Relicy and a few other things. He's done a bunch of the kernel address sanitizer, kernel thread sanitizer, done a bunch of really cool stuff. I had something that had more levels of indirection in certain cases than I needed. He showed a cute trick with pointer tags. Get rid of that, so we'll apply that here. I was proud initially of the fact that take a normal concurrent algorithm and just tweak a little bit, and hey, you can do atomic moves. But that was okay until I started trying to say, okay, how many of these stupid things I'm going to rewrite to have this little tweaks in it? And so this time around, we just have wrappers. So you take the algorithm, the data structure, pretty much unchanged. So you have the same algorithm you had before, and you apply a wrapper to it, and you do the atomic moves. Okay, so a little better code reuse. Now, this isn't quite as vicious as some of the people who take a straight sequential algorithm and apply parallelism, which is not transactional memory. Instead, what we do is we start with something that is a good concurrent algorithm, probably using RC on the read side. That's the ones I've done, but then, what would you expect from me, right? Then you apply a kind of a wrapper and get the atomic move on top of it. Now, the other thing is that the previous round, you had to manually clean up after things. And we'll show later on how that works and what has to be cleaned up. And that cleanup is now automated. So you just go through and set it up, and you say, do the atomic switch. And after that, the stuff gets cleaned up without you having to do anything extra. On the other hand, what this means, as you'll see, is we start from ground zero on both reliability and performance, scalability, and so on. All right? It's a new algorithm, and it needs more work. But you start over, you start over. Sammy mentioned that I've been doing this for a while. How many people were alive in 1990? Okay, so I'm not as out of date as I might have thought I was then. Thank you. Of course, I'm a little more out of date than I might like, but hey, you take what you get. Anyway, when I first started, what's the problem? Use a hash table, right? Have a lock on each element, on each bucket, everything scales nicely. You can read, you can write. Things are wonderful. Well, part of the reason that it was seen as a solved problem back then was that computer architecture was a little bit different. In 1990, it took about as long to execute an instruction as it did to fetch DRAM. The first machines I was working on had, I kid you not, a 16 megahertz clock cycle. And that was megahertz. It was 16. It wasn't gigahertz, So, in that time, you can do all sorts of things in hardware. And they did. And that meant that some things that you've heard about, memory contention, some of the cache miss problems, things like that our previous two speakers talked about, they were problems, but they were a lot smaller problems. If you have these really big machines we have now, where it may take a microsecond or so to get memory from the far end of the machine to the other far end, and you've got gigahertz clock cycles, life's a little harder. Anyway, so yeah, in theory and a long time ago, but even if you have a read-only benchmark and you're just doing locking, you can see the bucket, global locking, nobody expects it to do very well, but the bucket locking, that looks like a gentle drop-off, but that's a log scale. That's a cliff it falls off, all right? And this is a read-only workload, and we do have bucket locking. All right, well, if you got a hash table's got problems, what's the first thing you do? Adjust the hash function. We heard about the JHash stuff earlier, or increase the number of buckets. And that does sort of help, but once you get up to 16,000, we're not getting any benefit out of the increases. And also, there's still a drop-off. It's not like we're increasing. Now, in my view of the world, if I go from 8 CPUs to 16 CPUs, I want, more performance, preferably twice the performance, okay? And sometimes you get even more than twice. Superlinear scaling does happen from time to time. This just isn't the way the world is supposed to work from my viewpoint. So what's wrong? Well, we have a little problem with the laws of physics. Computers look kind of like this these days, sort of. You've got a bunch of CPUs, you've got interconnects, you've got memory, and the memory might be associated with the groups of CPUs or not. I just drew it this way because it was easy to draw. And the problem is that the speed of light isn't as fast as you might like. I mean, if you're going at 2 gigahertz, you get about that far over and back. Okay, so why is over and back important? I mean, well, the problem is you say, I want that data over there, the request has to go out, and then the data has to come back. And unfortunately, this is horribly optimistic. You see, last I checked, I mean, back in my dad's day, the innards were vacuums. They had vacuum tubes, all right? But the computer chips aren't vacuums. I mean, they're like silicon with impurities. And light doesn't go as fast through that stuff as it does through a vacuum. In fact, if you're lucky and a good conductor, you might get 30% the speed of light. And if you're talking about the innards of some of the transistors, maybe 3%. Plus, you've got clocking and a bunch of other stuff. I mean, it's not like you go through these different levels of caching just, like a speed of light. What happens, you get clocked through and things happen rather slowly. So what that means is you get about this far over and back in a clock cycle, and the chips are bigger than that. So we've got really two problems with the fundamental law of physics, and this is observations by Stephen Hawking after visiting, I think it was Intel Research, looking at some of their fab issues. The first one we've talked about, the finite speed of light. Light, as far as we know, only goes so fast, and we don't know of any way to make data go faster than the speed of light. Now, this is not mathematical. This is an empirical observation. So we don't know for sure that this is always forever the way it is, but I'm here to tell you, if you figure out a way around this, you've got some pretty serious recognition coming your way. All right? So, get on that, because this is really causing us trouble right now. The second thing Stephen Hawking called out was the atomic nature of matter. And this is kind of a cartoony picture of an atom, or excuse me, of an atom. There's some atoms there too, of a transistor. You got a source, a base, and a drain. And the thickness of the base, both the kind of electrical and the spatial distance, kind of controls the performance. In research labs, they've actually made transistors that look like that, with one layer of atoms as the base. I'm not sure what happens in production. This stuff's kind of a closely guarded secret, and I'm not in on it. But almost 10 years ago, I saw scanning electron microscope pictures of transistors, where they sliced the die in half and took a look at the transistor. And there were about that many atoms in the base, like 4 or 5. Now, we've had the technology to split atoms for a long time, but this tends to have a really bad effect on the semiconductors. We haven't figured out a way to make that work either. But there's another opportunity for you. If you can figure out a way to make something smaller than the atom work in this thing, go to it. We need your help here. In the meantime, we use softer tricks. The one that I've done a lot with, read, copy, update has the read in it, is read-only accesses. And the way that the computer systems work is if your data is read and not written, you can get replicas of it in each cache. And suddenly, instead of having to go across all the way to memory and back, you can just go a little ways and get at your data. All right? So read-only access and the cache replication is one way we have of circumventing the speed of light and the atomic nature of matter. It's mostly speed of light. The atoms are still there, unfortunately. Although, if they went away, I guess it'd be a problem. The problem is, though, as soon as you do an update, if the lower right-hand CPU does an update, you just blew away that value in all the other caches. So first off, that update was horribly expensive. And secondly, the next time the other CPUs go and read, that's horribly expensive too. So if you're doing that a lot, the extra CPUs are just getting in your way. And this sort of thing is one of the reasons why there was this massive amount of primal scream therapy around 2003, 2005, once people realized there wasn't a free lunch. The guys have been, like me, have been doing it for a while. So guys, what's your problem? Of course, but they didn't see it that way. So, okay. One way of dealing with that is to use something kind of like sharding. If the CPUs are all operating on different data, and it doesn't have to be a perfect split, you just have to have a high probability of working on disjoint data, then again, the caches will just keep that CPU's data in that CPU's cache, and things will go fast. Of course, you can still get in trouble. You don't want the data for two different CPUs in the same cache line, false sharing. And you've only got so much cache, so you want to be careful how you use it and so on. But you can do really well this way. And again, you don't have to be perfect. It's not like we're going full distributed programming here. You just have to have a high probability. Of course, the higher your probability of not having your own data, the lower your scalability is. But it's a trade-off. You know, how much scalability do you need? All right. So we've got a couple ways of dealing with it, and on the next slide we summarize those. The biggest thing is, you know, don't write to shared memory unless you really have to. All right? Don't just go writing to shared memory because some, you know, programming methodology says you should. All right? And the thing is then what that means is if you're updating a search structure, and we'll look at this a bit more later, you shouldn't go updating the upper part of the search structure just because you might update the bottom part. You know, leave the upper part alone, let other people get through it at the same time, and do your updates where you need to do your updates. The other thing is you want to try to split things out a little bit, and you want to try to give CPUs separate data. One of the big things we use in the Linux kernel, and it's been used in a lot of applications, it was old back in 1990 when I started programming. I don't know who came up with it, I haven't been able to figure it out, but when I was starting with Dynix PTX in 1990, having a split counter where each CPU or each thread has its own value, and it just adds to its own value, and you sum them up to get the statistical output, that's been around for a long time, and it's a way of making this happen. And there's a bunch of other techniques like that. Okay, this is also one reason why hash tables aren't necessarily the perfect answer to all solutions, all problems. If you have a hash table, it's kind of difficult to do range partitioning. You can do it if you know the hash function, you give each CPU its own piece of the hash function. But sometimes algorithms aren't as friendly to that sort of splitting as they might be, okay? And if you do need to worry about the ranges explicitly, then tree-based structures will do better for you. If you can avoid rebalancing them, because we haven't found a good way to do that yet except for skip lists. All right, so let's talk about the read-only traversal to the update location. And the classic methodology for this sort of thing would just lock the root, find the descendant, lock that, and keep working its way down. And this is just, again, is not going to be a solution to the Issaquah problem because everybody's locking the root. It's also not going to be any kind of thing that's going to scale because everybody's locking the root. The lock contention there is not going to be pretty. You might be able to get around it with something like the lock collision techniques with some of the Harvard transactional memory things, maybe, depending on what you're doing. But those often have limits in the amount of stuff you can put into a transaction, and those limits may be inconveniently small, depending on what you're doing. So you'd like to not do it this way. Now, that's why we have RCU, and so there's other techniques. Last I was able to check, there were something like 8 different independent inventions of something kind of like RCU over the years. And there's a bunch of other things kind of like it too. Garbage collectors, you can use those like RCU if you want to go back to the 50s. Hazard pointers, Megan Michael, I think, is going to be talking later on at the conference, and that's his approach to it. Reference counters, you're really careful. Reference counters, you're writing to shared memory. Might not be what you want to be doing, but if you manage it carefully, you can make it work, and various other things as well. And the idea here is you want to avoid the expensive shared operations on the read side. And so, you know, there's a guy that I knew back in the early 90s. He had, you know, long white hair, big white beard, kind of looked like Gandalf a little bit. And he had a sign on his cube. And the sign said, only those who've gone too far can possibly tell you how far you can go. So in that spirit, I'd like to suggest going all the way, all right? We can always back off if it's a problem, right? You know, we got git, we can do git revert, it works, you know, so it's not quite like some other endeavors in human life where things may be irrevocable. So I'm going to suggest # define RC read lock, new line. And # define RC read unlock, new line. And these are the things that guard readers. So you do RC read lock, and then you do a bunch of stuff, you RC read unlock. Now again, this is kind of empirical. It may be a failure of imagination on my part, but until something proved me wrong, it'd be really cool if you could, by the way. I'd really like to see that. But until you do, I'm going to assert this gives you the best possible performance, scalability, energy efficiency, real-time response, and also weight freedom. You know, it's hard to find something faster than doing nothing. But again, I'd love to see a counterexample. Negative overhead would be really nice. I noticed some puzzle expressions out there, and there certainly is a good question associated with it. Maybe you're worried about something else, but you've got this thing that is making absolutely no change to the machine state. It's worse than that, actually. This is C, right? This is a preprocessor symbol. We're not even getting anything to the compiler backend, let alone generating any instruction that would change machine state. And so a totally reasonable question is, if you're not changing machine state, how can you possibly synchronize? We'll get to that. I will point out that in the Linux kernel, if you select a server build, config preempt equals n, you get exactly that. Although there's some debug in there, it's not obvious, but if you look at what happens when you rebuild it, that's what you get. So how can we do that? I'm just going to give a quick overview of this. I'm going to run through it pretty quickly. There's some references into the slide set and a bunch of other stuff out there. But what we're going to do here is we're going to look at a change of state that adds a data structure to a linked structure here. It's very simple. We just have a pointer, this CPTR thing. And we're going to add a structure to it. We're going to take that in 4 steps, 3 state changes. We're color coding this. RC read lock doesn't do anything, and that means it can't block updaters. And updaters can't block it. And so the pointer is something anybody can grab at any time, so we're coloring it red. If there's something red, that means you need to be careful because a reader might pick up its value anytime. There's no way to stop them. There's not even any really useful way to tell where they are, that they're there or not. All right, the green stuff, the readers can't see, at least if your memory allocator is working at all. And so the updater can do whatever it wants with those anytime it wants without affecting the readers. So in the kernel, we do a kmalloc or a malloc or a new or whatever you want to call it. We get some memory. It's uninitialized. We initialize it. So far, so good. And we have to use RC assign pointer. Both compilers and hardware can reorder things, and this defeats that. And once we do that, suddenly readers can get at this memory. Therefore, the change of color from green to red. And then readers use RC to reference, which also defeats compiler optimizations and, in the case of alpha, hardware optimizations. If you don't use both of these, what can happen is the reader can come in and see the pre-initialized value. So these guys are mostly doing compiler directives, or possibly in the case of RCU, assign pointer on weakly ordered machines like Power or ARM. They're also doing memory barrier instructions. Okay, so what we got here is we've got a way to insert a new data element into an existing structure at any time, despite the fact that readers are traversing that structure. And we're getting kind of a limited degree of safety. Because that store is atomic, it's just a normal store instruction, nothing fancy about it. But the thing is, if you do an aligned pointer-sized store on any architecture that the Linux kernel supports, there are some other exceptions, some older machines, then a reader loading from that same location is going to either see the old pointer or the new pointer. It's not going to see some mush of the 2 pointers. If you did see a mush of the 2 pointers, then life is very bad. Because of that, you either see there's a new structure, and if you see it properly initialized, or you conclude there isn't one. But either way, you see something valid. And that level of consistency turns out to be adequate for a surprising number of situations. In addition, it's possible to recover a higher degree of consistency if you wish to after the fact. Okay, so we're kind of halfway there. We can insert new data elements into existing structures despite the fact that readers are flying through them unimpeded while we're doing it. But of course, if that's all we can do, we got a big memory leak. And for some applications, that's okay. They run for a while, they just restart the whole thing. And they could just do something like this and just never free any memory that was removed and be happy. But if you want to get rid of the memory, if you don't want to be a big memory leak, then you have a little more of a challenge. So again, we have 4 states and 3 changes. Time is going to advancing from left to right. And we're having a little more complicated data structure. We have a linked list. And we want to remove the cat. All right? So the first thing we do is just rely on the fact that the pointer stores are atomic in the sense we discussed earlier. So we take the next pointer of the boa and make it point to the GNU in one store. So suddenly, old readers can see the cat, but any newly arriving reader has no path to it and cannot see it. All right, so at this point, there might be readers referencing the cat. Maybe for an arbitrary length of time, they might get interrupted, they might get preempted, who knows. But no new reader can see it. So if we had some way to wait for only the old readers, we don't have to wait for the new ones, they can't get to the cat, we just have to wait for the old ones. If we had some way to do that wait, then after that wait was complete, there'd be no readers referencing the cat, and we could just get rid of it, or overwrite it, or do whatever we wanted to it. So if we want to avoid the memory leak, the key thing we have to do is be able to wait for old readers. And it turns out that this is possible. There's a number of ways of doing it. There are some important ways that allow the readers to be totally free, as we discussed, and some other ways in other environments where the readers have to pay some cost. But the operations they do are totally local and very simple instructions. Let's talk about the free one first, since we're here. And this applies in the Linux kernel where config preempt equals n, as mentioned earlier. I'll do the other side now just to try to be equitable, or to avoid wearing a rut in the carpet. Okay, so in a non-preemptive environment, one of the rules you have to follow is that if you hold a pure spin lock, you're not allowed to block. Okay, pure spin lock, you're going to spin until you get the lock. And you're going to keep spinning until you get the lock. And if you don't get the lock, you'll spin forever. All right? So if you hold such a lock and block, the bad thing that could happen is that each CPU might start spinning on it, at which point they're not going to give up the CPU until they get the lock, and you're not going to give up the lock until you get a CPU, and so you have a deadlock. As a result, we have the rule. If you're in a non-preemptive environment and you have a pure spin lock, if you're holding a spin lock, you don't block. So what we're going to do is we're going to apply that same rule to the RCU readers. Once you've done RCU read lock, you're not allowed to block until you do the corresponding RCU read unlock. So that means with that old list we saw, with the GNU, the boa, the cat, and the GNU, you start traversing it and you don't block until you've completed your traversal. And what that means is that as soon as you see a context switch on a given CPU, you know that that CPU has completed all its prior readers, because you're not allowed to block in the middle of read-side critical sections. So these blue arrow things are read-side critical sections. We have an RC read lock at the beginning, we have a bunch of code that doesn't block, and then we got an RC read unlock. You're not allowed to block in there, so if you do block, well, just the wait blocks here. We block here and here. Once we get to this vertical line at the end here, we know that all the CPUs have context switched. And therefore, all the CPUs have finished any read-side critical section that had a chance of seeing the cat being removed. So once we've seen each of those CPUs context switch, we know it's safe to free the cat. So as a result, in a non-preemptive environment, as in a kernel build for servers for the Linux kernel, we can have the readers do nothing and still concurrently add and delete data to a concurrent data structure. Okay, so let's go back to the question about machine state. They don't need to act on the machine state. What they do instead is they act on the developer. The developer has to follow the rule. If I'm in a read-side critical section, if I've done an RC read lock and I haven't got to the matching RC read unlock, I'm not supposed to block. As a result, RCU is an example of synchronization via social engineering. It's true. You know, the thing is, though, that every other synchronization mechanism has a social engineering component. Every one. And there's examples there. I'll just pick on the last one. You know, transactional memory. Well, it's got this nice mechanism. There's hardware, there's software mechanisms. But, you know, if you use it and you don't follow the rule, the data you're protected by transactional memory has to be in a transaction, it's not going to work. So every mechanism out there, every synchronization mechanism out there has a social engineering component. The thing that's unusual about RCU is that in some implementations, there's nothing but social engineering. And social engineering runs really fast on the machine, and that's one of the things that helps. Of course, as a result, RCU is specialized, and the specialization is what gets us its strength in some sense. It works best when you mostly are doing reads. You have a data structure that you're going through and reading, and only occasionally updating, and where it's okay to have inconsistent data. This turns out to be very common and has been getting more common. In the early 80s, when I was using Unix, if you wanted to change the hardware configuration of the machine, you had to rebuild the kernel. If you wanted to add a floppy drive, you rebuild the kernel. And well, there was only 64K of memory on the thing, so it wasn't like we had memory to throw around keeping track of what was on the machine, and you just had to build it in hard. That's the way it was. That's changed. We got more memory. We got more sophistication. We got machines that have plug and play of various sorts, so you can tell whether something's there or not without just having to know. And so we've got a lot more data in the machine that reflects the external state of the universe, what hardware is plugged into it, what the state of the internet is, and so on. Thing is, we get the speed of light again. In this case, is on our side in some funny way. If you're tracking external state, your in-memory data is out of date, period, end of story, guaranteed. It takes time from the time the external state changes until that's communicated to memory. So in the case of internet routing, it's probably the poster boy for this. To prevent various kinds of pathological things, routing circuits and things like that, black holes, what they do is they deliberately slow the propagation of routing updates through the internet to avoid inconsistencies and avoid oscillations. That means by the time a routing update reaches your machine, you've been sending stuff the wrong way for many seconds, maybe even minutes. So who cares about another few milliseconds? So that's the blue chunk. If you need consistent data, and that's another common case, it's read mostly, but you need to, and things like System 5 semaphores, where they use RCU to map from the ID, the user space ID, down to the kernel data structure. It's not nice to do something to a semaphore that's just been removed, so you need the consistency in that sense. But we get it after the fact by having a lock on the structure itself. Okay, so that's the green section. Things work fairly well there. Path name traversal. This is probably one of the more complicated uses of RCU I know of anywhere in Linux kernel. There, things can change quite a bit. We need consistent data. It's not okay to open a file after it's been removed. All right? And RCU can work in that situation, but it's complicated and somewhat difficult. In the worst case, where you are only doing updates and you need consistent data, you probably have something better than RCU at your disposal. There are a couple of exceptions. They're listed there, but for the most part, if you're down on the bottom, you want to use something else. Okay, so with that in mind, let's look at the read-only traversal to the update location with the idea we're not going to write if we don't have to. So what we're doing here is using RCU again, and that means when we free anything part of this, we're going to have to delay until the readers are done, any old readers are done. So we do RC read lock. We start at the root without locking. Okay, we're not allowed to block while we're doing this. We just go plowing through. And we use key comparison selected descendant. We repeat until we've reached the update location. And at this point, we acquire locks on the update location. Of course, other people might be changing it while we're doing this. And so we have to be careful. We have to check. For example, we might acquire a lock on something that's just been removed. We went to it, and just as we were acquiring the lock, somebody else removed it out. They held the lock already. So we got this lock held on something that's no longer connected. And as soon as we leave a restart critical section, it will disappear. But for right now, we're in a restart critical section. It's guaranteed to stay there. We're staring at it. So we see that if the flag is set, we say, OK, fine. Let's just start from the beginning and try again. Otherwise, we carry out our update and then release our locks and exit the restart critical section. So what we're doing in a sense is we're starting at the top, we're going down and using RCU to protect us. When we get to the bottom layer, we use locking. And that way we're not modifying the upper levels of the tree, and those are the parts that are read most often. Everybody looks at the root, and it is rarely changed if you're tree is balanced at all. Okay, so we can use this trick. And the idea, again, is to focus contention on the part of the structure you're actually updating. Don't update stuff you don't have to. And of course, it's still better to fully partition if you can. This has been around for a while. In fact, you can go as far back as 1980. Pugh and Kung and Lehman, excuse me, wrote something where they're using a garbage collector, essentially, in the way that I'm using RCU. And so this is an old idea, but it's still quite important. And therefore, one solution to the Issaquah problem for a binary tree is to just split it out like we did with RCU, protecting the top and locking at the bottom. And we're going to use existence structures to mediate the atomic moves. Now, as I mentioned earlier, once you get the locks, you have to check for bad things happening. And here are some of the bad things that can happen. Okay? You might go and get the lock on the node you want to do something with and its parent. Okay, for move it, you need the parent and the child. They might both be gone. Or maybe the parent's gone and the child's moved somewhere else. Or maybe the parent's there but the child's gone. Or maybe somebody's been stuck in between them. If any of those happen, you can't really update. You're holding locks that aren't relevant anymore, and you need to retry. The key thing is, and this is what I did in the LCA thing a little over a year ago, is I relied on this and put things together and made this work. The key thing is that you don't need to be doing moves to have this problem. If all you're doing is adding and deleting elements, you have to make all those checks. The tree might grow, things might be deleted while you're trying to delete them, and so on. And so that opened the possibility of doing this in such a way as to avoid the need to modify the underlying algorithm. Use the algorithm as is and apply the atomic moves and atomic updates, the complex updates on top of it. And we do that, as is tradition in computer science, by adding another level of indirection. In the old days, I added 3 levels of indirection, which I'll skip over, and we'll go to Dmitry Vyukov's modification. So what we're doing, I'll switch over to this side again. We have a data structure and A and B. And in this case, we have an existence pointer as part of it. Normally, this pointer will be null. And a null pointer says, I'm here. A non-null pointer says, I might or might not be here. And what happens is the pointer points to this existence switch. This switch is a simple integer, it might be 0 or 1. And next couple slides will show how that works. And if the bottom bit of the pointer matches, then the element exists. If it doesn't match, it doesn't. And we'll abbreviate this way, going through an example a little bit later. Mostly because if I tried to draw the whole thing out, it'd be a mess. Some would say it's a mess anyway, but life's like that. Okay, so in this case, the existence switch is 0. The value is 0. Therefore, anything with the bottom bit of 0 exists. Something with the bottom bit of 1 does not exist. So data structure A on the top currently exists. Data structure B is in the data structure, but is marked to not exist. All we have to do is store a 1 to that yellow box, like that, and suddenly it switches. Now, the value is 1, and therefore suddenly data structure A no longer exists, and at the same time, data structure B suddenly starts existing. Thing is, we could have as many data structures as we wanted, referencing the same yellow box, the same number. And so we can change one number and make an arbitrarily large change to the data structure. And that's the basic trick. And we're going to show that. We're going to use a box with a 0 and 1 and red and blue. Red is the one that doesn't exist, and blue is the one that does. So we'll switch it back and forth. And we'll show how it works in the old original challenge with a tree. So initially, we have the tree with 1, 2, 3 on the left side and 2, 3, 4 on the right side. Now, all the existence pointers everywhere are null, so everything that's there is there, and if it's not there, you can't find it anyway. So the first step is to make an element 4 for the left-hand tree and an element 1 for the right-hand tree. They aren't connected yet, so you still can't find them. But we also hook up the old elements 1 and 4 to this existence pointer setup. And it's set up now so that 1 and 4 exist, and the ones you can't get to anyway don't exist. We can take our sweet time making this update. The readers get the same answer. Before we make this change, they see a null pointer and say, great, this thing exists. After the change, they see a non-null pointer, but the bottom bits match, therefore it exists. So we don't have to make this change from slide 46 to slide 47 atomically. We can do it incrementally over time. Has no effect. The next thing we do is we link the new 4 and 1 into the tree. Again, we can do this non-atomically. All that happens is that we take longer to get the answer. Back before we link them in, on slide 47, we say they're not there because we can't find them. There's no pointer to them. After we link them in, we say they're not there because the bottom bit of their pointer doesn't match the current existence counter. So either way, they don't exist. We're just making it take a little longer to get that answer. So we can do that step again. We do that second step non-atomically. The next step is to switch the counter. We do this with just a single store. It could be just a single byte if you wanted. So this is atomic in the sense that nobody sees a mush of the two things. And even if they did, it's only one bit difference. So either way, they'll see something valid. And so suddenly, element 1 in the left-hand tree ceases to exist. At the same time, element 1 in the right-hand tree exists, and vice versa for elements 4. So we've done an atomic move of element 1 from the left to the right. At the same time, we move 4 from the right to the left with just this one store. All right, so that's how we get the atomicity. One thing we pay for this is that our lookups are going to have to use memory barriers if they want to see consistency. And if they don't see consistency, there's no point in it being atomic, right? So it's not totally free. Then we can just clean up the data structures. Again, this can be done non-atomically. On slide 49, we decided that element 1 wasn't there in the left-hand tree and element 4 wasn't there in the right-hand tree because the existence counts didn't match the bottom bits and the pointers. When we go to slide 50, we say they're not there because we can't get to them. So that can be done non-atomically, it can take a while, and we can also do the cleanup afterwards. And one thing we're adding to this approach to it is we're making it so the cleanup is automated. So you just set things up, and when you do the flip, it goes and cleans things up for you. Let's go through this again. Each data element has an existence pointer. Null pointer says I'm here. Otherwise, we have a pointer tag, and if that matches the location referenced, then it exists. If it doesn't match, it doesn't exist. Of course, this means you better have a good API for this, because I don't know about you guys, but if I have to do null pointer comparison and it being equal null means it's there, I'm going to get that wrong every time, all right? It's just, so you're going to have to wrapper that with something, because that's just not going to be fun to do that open-coded. Let's start with the data structures. I'm not going to go through this in great detail, but I'm going to go through what we have and what effect it has. This side again. So existence group is that yellow box, all right? And the state, e.g. state there, which is, it's an integer because we have to set bits in it, and setting bits and pointers in C and C++ is undefined, so we make it be an integer and cast it as we need to. That's the thing that's, that has the, either has a 1 or a 0 in it, all right? It's a state we point to. The e.g. outgoing thing is a linked list containing all the structures that are going to disappear, and that linked list allows us to do the cleanup. We just traverse the linked list, and we, if we're outgoing, we're going to free up the data structures that are no longer in place. We have to get rid of the data structure as well. We'll get to that in a minute. Incoming, we're going to clear their little pointers with the bottom bits because they're there now. They aren't, and so we just clear them so the next operation can happen. And then the RCU head just allows us to RCU free it. It's not involved, but directly in the algorithm. As part of each data structure, we have this existence head structure. And so you have your normal structure, you have it, we'll show that in a moment. We have an uint pointer that is the pointer, essentially, to the e.g. state field. And it's either got its bottom bit set or not, or it's entirely null if this is permanently there. We have a list head that allows us to be linked into the e.g. outgoing or e.g. incoming fields. And then we have the three things that allow this to be applied everywhere. If you want to apply this to a concurrent data structure, you have some way to add an element, you have to remove an element, you have to free an element. Okay? And however you do that, you can do that. This algorithm doesn't care, as long as you give it a function pointer that allows it to do that. Or if you're using C++, probably use templates or at least overloading. There's a gone field that says I'm not here anymore that allows us to detect somebody changed it and we should back out and retry. We have a lock to allow if multiple people get in and want to do something to this, the lock mediates that. The first guy wins, the second guy loses and has to do something. And then again, we have to RC free these to help the readers. So that's the data structure. It's not very complicated. I'm not going to go through in detail through the API, but it's kind of what you'd expect. You can initialize an existence group. You can get the incoming or outgoing flavor, so you can store it into the data structure that you want to appear or disappear. And then you can find out something exists. You can set and clear the field. And you can test to see whether it exists. You can do that with ordering or not. And then you have initialization for something that's going to come into the data structure and go out of the data structure. And you notice when it's incoming, you tell it what the operations are. When you're doing outgoing, it's already there, so it's already got the operations. You don't have to tell it twice. And then you can either flip at the second to bottom to commit the change, or you can back out to say, I ran into a problem. I wanted to delete an element. It's already deleted. I can't do this operation, so I'm going to back out and either give up or try again. Okay. And this is how you put things together. If you had things, and this works for arbitrary data structures. The place you're going to and the place you're going from don't have to be the same type of data structure. So you have your two data structures. You have the header for that data structure, whatever it is, the thing that allows an element to be part of that data structure. Then you have the existence head structure we saw earlier, and then a user pointer that points to the data element. You can also, if you have a small element, actually just put it in the structure here, which is what I did in the past. The disadvantage of that is it makes it tough if you're trying to move from, say, a hash table to a linked list, which would have totally different headers. You can get around that if you want to by just having multiple headers, one for every data structure you might link this thing into, but that can get a little bit ugly after a while. So this is how it's linked up. We have this is a member of data structure 1, this is a member of data structure 2. We have the existence group structure. This guy currently exists, so his bottom bits of his pointer match the value. This guy doesn't exist, they don't match. And then once we change the existence structure, then this user data element has been atomically moved from one structure to the other. And they could be different types of structures. Okay, so then if you want to do atomic move, this is kind of pseudocode for it. This is the old style. What I'm going to look at is actually something a little more ugly, I guess, or complicated or something. We're going to have 3 hash tables. Those are the green boxes, hash table 1, 2, and 3. And we're going to have 3 elements. They're at the bottom, 1, 2, and 3. And what we're going to do is we're going to rotate these things through the hash tables. So initially, we have element 1's in hash table 1, element 2's in hash table 2, element 3's in hash table 3. We're going to atomically shift them so that element 1 is in hash table 2, element 2 is in hash table 3, and element 3 is in hash table 1. We're just going to keep doing that, shifting around and around, and that's kind of our exercising benchmark for this method. So we create these incoming and outgoing things, the red and the blue. The blue is the current state, the red is the incoming state. We have this structure on the bottom. We do the switch, and suddenly they change state. They all move atomically to the next hash table in sequence. That cleans up the outgoing state, and then we can just do that again, making a new incoming state and keep repeating that. There is a little overhead. We are allocating and freeing 7 data structures every time we do a switch, but so it goes. And we again have a data structure. We have the key value, which is it's a very simple thing. It's just a key and a value along with a reference count. We need the reference count. If we're going to delete it, we want to figure out when we delete it as opposed to moving it. And then the actual structure, the incoming, the outgoing piece, has the element for the hash table. It has a pointer to the hash table, so you know which hash table is a member of at the current time. And then you have the existence header that tells it whether it exists or not at the current time, and then a pointer to the key value. All right. And then sort of pseudocode for a rotation. We allocate the new existence pointer, make sure it's there. We initialize it. In a read-side critical section, we allocate the new incoming members. We tell them which one is the key value is. The tilde zeros are just saying that it already exists. We don't have to give it a key and value. And then we set outgoing for the ones in the old hash table. And then we can get out of reset critical section. We do an existence flip, and they change state suddenly. And it also cleans up the outgoing data structures. And then we can do call RCU to get rid of the existence structure we had. The incoming and outgoing structures that have to be reaped are reaped automatically by existence flip. Of course, if you, in this case, I did a thing that didn't have contention. You normally wouldn't have bug on, you'd have an if. And if the existence set outgoing were to fail, that would mean the node was deleted while you were trying to move it, or maybe somebody else was moving it somewhere else, and you'd have to back out and see what you wanted to do in the new world where it's gone. All right, and this is, I've implemented and run this, and it runs in a hash table that was written before I had any idea you'd do atomic move. All it supports is inserting and deleting elements and looking them up. It doesn't support any kind of atomicity. The atomicity is added on top. Okay, a bit about performance. I mentioned at the beginning that we were starting over and life wasn't all that good. I'll quickly review what we had before, and read side still works fine. There's nothing in its way. Mixed benchmark, I didn't run this time, didn't get time. This is what we had for update only for the worst case. And if we expand it to 60 CPUs, we're getting sort of semi-reasonable scaling in the old style. Okay, well, how about the new style? Okay, well, for readers, I said before, it's as good as ever. For the triple hash rotations, initial results were actually pretty bad. All right, this isn't surprising. For one thing, we are in the situation at the very bottom. We're doing nothing but updates, and that's not what RCU is designed to do. But, you know, this is an opportunity to improve the infrastructure. Just because it wasn't intended to work in a particular way doesn't mean you don't make it work that way, right? Now, with apologies to any Kathleen Turner fans who might still be alive, if you're trying to make a perfectly scalable algorithm, there's probably 50 things that go wrong. If you're a genius, you might be able to foresee and forestall 25 of them. I haven't found very many issues thus far. That means there's a lot left, all right? But there's the usual things like alignment, which results in false sharing. Easy fix, just add the alignment directives. You have to configure user space RCU correctly. If you want it to work well, you need a separate thread for each worker thread to keep up with the rather high rate of freeze going through it. We had massive contention on locks. I used a fairly simple perf thing and saw that futex was rather high, as we saw in the previous thing. That's a bad idea. Now, one thing is I might have just misdesigned the benchmark, or I might have missed my data structure. One easy way, really easy and kind of stupid way to take care of that is all your lock acquisitions, replace them with tri-lock. And if the tri-lock fails, just abort, all right? And that'll, if you've got any lock contention at all, you'll find out about it really quickly. So I did that, it ran to completion, no problem. So, okay, there's lock contention, but it's somebody, somewhere else. Well, I could just say, not my problem, but scalability is a system-wide thing. And if you're trying to make something scale, you're taking responsibility for the full system. It turned out that the memory allocators were biting me. glibc you expect to bite you. It's not written to be scalable at all, really. But JEmalloc and TCmalloc are supposed to be fairly good, except that what was happening is JEmalloc was increasing its resident set size forever. TCmalloc was getting massive contention on the global pool lock. TCmalloc is supposed to have a better version that has per CPU pools. Paul Turner and I've lost the other guy's name are working on it, but I've heard about that a long time ago and haven't seen it, so waiting for it might not be appropriate, especially as the talk was today. I have some experience with memory allocators, but I came across this yesterday, I think it was, and so I chose a quick hack. And what I do is I just have queues, so then I pipe back from the people who are freeing it to the people who are allocating it and just run the memory back to the right place. And when I do that, I don't see the allocator as a real high hitter anymore, so that's good. But I see user space RCU callback as being a high hitter. That's no surprise. I wrote that. I did not write that with this sort of workload in mind. It needs some help. I didn't have time to give it that help before this talk, but that's the next step. And it's quite likely it needs some of the techniques from the kernel. We had this kind of problem in the kernel and had to rework things. We probably have to rework user space as well. So the scalability at this point for this update-only triple hash rotation is not great, but it does at least sort of scale for a few CPUs. So we're at least on the right track given the point we're at in re-implementing this thing from scratch. Disadvantages. Existence is not magic. You have to make some changes, okay? And it's specialized link structures and so on. But it's something that actually is fairly simple to apply. And it really makes a mean allocator and user space RCU test. So it has things there. I really don't know what you'd use this for yet. This was a challenge and something I've done as kind of a part-time effort. If you know if something's used for, let me know. I have some ideas at the bottom of the slide where it might be useful. Production readiness, it's not, okay? And not only is it not, but with the Internet of Things, we got a real problem on our hands. Most of my effort the last several years has actually been validation and verification of the Linux kernel RCU, because if I have a million-year bug in Linux kernel RCU, you're going to have to write a real tough test to find that. But it's happening several times a day across the installed base. There's something like 1.4 billion, that's billion with a B, smartphones, Android smartphones. And every one of those has RCU in it. And there's a whole bunch of household appliance servers and loaders, what else? And so I need to raise my game. But the existence space stuff isn't even in the running for that sort of thing. It's, at this point, a toy. So if you use it for production, allocate some time and space to fix it because it needs some fixing. This is just some things that have been around that sort of lead to this in some way. And finally, we can do complex updates. We can do that with existing concurrent data structures. We don't have to modify the data structures or the algorithms. We can automate the flip and back out processing. And the high update rates find bottlenecks, which I'm in the process of fixing. And of course, there's lots of opportunity for collaboration, innovation, and so on in this area. I've got several pages on what you want to do if you want to probe deeper, and we've probably got time for the IBM Legal sponsors that page, and we've probably got time for a question or two if people have them. If not, enjoy your lunch. I think, was lunch on the third